Okay, it's early in the morning here, so I will tell about new stack, and please feel free to interrupt me and ask questions, so it would be easier for me to answer them just as they arrive. Okay, let's start with the hardware. We have ST25R3916 chip connected to our NFC board, and we use this chip in two different modes. Let's say it's FIFO mode and transparent mode. When I say FIFO mode, it means that we can configure the chip and send some SPI transaction to fill the FIFO, and the chip itself will form the NFC signal and transmit it, and the same for receiving part. So the chip will detect NFC frame, parse it, and put it in FIFO, and Flipper can read it. So talking about this mode, the chip itself supports these features. So the NFC A polar and listener, NFC B just for polar part, Felica for polar and listener, and NFC V signal just for polling. A couple of words about terminology. When I say polar, I mean that Flipper acts like a reader, so it can read the NFC tag and write it. And when I say listener, it's about emulation part. So the Flipper can pretend to be a tag. These features are come from the box for this chip in the FIFO mode. And there is also a transparent mode. The transparent mode is a special mode that provides you the interface for modulator and demodulator. So basically, using the GPIO, you can form the NFC signal itself, and you can receive the NFC signal from another GPIO. So in theory, using this mode, you can implement any protocol. So let's talk about connection. The Flipper the connection between the Flipper MCU with this chip is just a SPI, common SPI connection. So we have 4 lines for SPI. It's chip select, master output, slave input, master input, slave output, and clock. And also there is a IRQ pin. This pin is raised by the chip when there is some kind of event to be processed. We use this SPI connection in the FIFO mode, and in transparent mode, these lines behaves a little bit differently. So if we enter the transparent mode, on the master output slave input line, you can toggle the pin, this pin, and you will have you can modulate the NFC signal manually. So by toggling this pin, you can control the modulation. Also in transparent mode, you have the signal on master input slave output pin and IRQ pins. These signals corresponds to on-off gain demodulation and amplitude shift demodulation. Also, there is one pin called MCU clock. Unfortunately, we didn't connect it to the main board, to the MCU. And this signal in transparent mode, it extracts the clock from the carrier frequency. So in transparent mode, for example, if we are in listener mode, we have exactly 1356 megahertz signal on this line. Okay, it's all about connection. So a couple of questions. Why did we decide to refactor the NFC subsystem? As Alex told previously, so previously we used the Rafal library. It's a library from ST company, and there were some issues with this library. So the major one is that it's not designed for ROTOS, real-time operating system. Basically, there was just one function called Rafal Polar, and in order to make some transaction or basically run the NFC stack, you have to call this function as frequently as possible. And it's not exactly compatible with multi-thread architecture as we have. Another issue is the lack of layer separation. So basically, in this library, you have one big file and all layers starting from the low layers and up to the protocol layers. You have all in one file, and it's really, I would say, write-only code, and it's very hard to maintain and expand. Okay, I put here another disadvantage is bad quality code, but it's my opinion. I think it's not correct to say that. But okay, in general, this code is very hard to expand, maintain, and so on. So
just to interject, I've looked at that code before myself, and that code looks like it was written by a hardware engineer, which I think calling it bad, I agree, is kind of a hard thing to say. But let's just say not written by a software engineer who is looking for modularity and extensibility.
Yes, I agree with that. Okay, so after that said, we have some requirements for the new stack. So first of all, it should be fully event-driven. It means that we have to, when performing some work with NFC, we should spawn another thread, and it should be suspended all the time unless there is some event occurred. Also, another requirement is explicit layers. So the full stack should be divided into explicit layers, from driver part to hardware abstraction layer and up to the protocols. And we really want to build a clean API for a new NFC stack. Okay, now let's have a look on the quick overview of architecture of new NFC stack. So the low part is ST25R3916 driver. This part is all about defining the registers for this chip and give functions to read, write, modify these registers. The next layer above is hardware abstraction layer. So everything that is hardware specific should be placed in this layer. After that, there is a worker layer. So this is the layer where we spawn a separate thread. And this thread calls functions from FuriHal and actually spawns other events for the upper layers and control the hardware. The next layer is the protocol layer. So here we have NFC device module, which is responsible for data management of the protocol. NFC polar for the polar protocol part, and NFC listener for emulation part. Also, there is a helper called NFC scanner, which helps to detect different protocols. So this is the upper layer for NFC stack. And NFC application call functions from the upper layer. So it calls this function, process the events from this layer, and give some commands to control this layer. So what protocols do we have? We have some base protocols. It's ICO.
Can I stop for a second?
Yes.
So for NFC worker, so in any event-based system, you have event loop. So the idea is NFC worker thread will run event loop. So that is the most important thing that you have to think about the worker. Also, since we have multi-threaded environment, in order to be as strict with timings as possible, this thread got elevated scheduling affinity. So it will preempt other threads if anything happens, if any signal will be received for it. That's it.
Yes, thank you. So the protocols we have, they are placed here, and they have a some kind of tree architecture. So we have NFC-A or ISO 14443A polar. This is a base polar. The NFC-B, Felica, NFC-V, and ST25TB polars. And there are some protocols that based on these base polars, like MIFARE Classic, Ultralight, and ICO 14434A, based on okay, let's say ISO 3 polar, and MIFARE Disfire, which is based on ISO 4 layer, and another protocol SLIX, which is based on an ISO 15693 protocol. Okay, now let's dive into the code. We will go layer by layer and talk about it in details. Let's start with the first layer, the driver part. Okay, can you see the code now?
Yep.
Okay, the driver part is very simple. So we have just 4 files. The reg files. Here we have the definition of the registers. Yes, of the chips. And we have some functions to control these registers. So just read register, read burst, write, modify, and so on. So it's really simple. All of these functions takes the SPI handle bus as an argument and perform operations with this register.
has entered the chat.
Sorry.
Oh, no problem. Okay, moving on. We have another file here. So it can be considered as a shortcut for the register operations. So, okay, there are not so many functions, but okay, if we want to write FIFO or read FIFO, actually inside there are just some calls to write or read registers. So you can use these functions to operate with registers in a simple way. Okay, it's all about the driver part. Now let's go to the next layer. Okay, hardware abstraction layer. The public API, let me open this file. The public API is available at furihal nfc.h. Okay, I will not go.
Sorry, you say AP, right?
API.
Okay, no, I mean it's just a language difference, but I was like looking for something that said AP, and I'm like, oh wait, no, I know this one. Okay, please keep going.
Yeah.
Okay, how it's to call correctly?
API.
API? Okay,
Yep.
I'll call API. So we have the initialization functions and also some low-level stuff, low-layer stuff like entering and exiting the low-power mode for the chip, the chip configuration for different modes. So we have the polar mode, the listener mode, and some technology listed here in this file. So if you want to configure the chip for NFC A or NFC B, you call these functions. Okay, there are. I will not tell about everything here because the most interesting part will be further. So in general, this API, so you can see the public API here, which is called by NFC worker thread. The NFC worker know nothing about the implementation for the hardware abstraction layer, so it calls these functions, and basically, if we want to, for example, switch to another chip, we can take this part, take this interface from this file, and implement it for another chip, and the NFC library will work as previously for the new chip. A couple things to say about HAL. So there is some technology-specific hardware HAL. Let me show it. For example, we can take 14443A and have a look at this implementation. So we have a private API here, which defines the function for the HAL hardware-specific implementation. So basically, when you call, when you want to configure the chip with NFC A or NFC B or something else protocol, you will eventually call these functions. For example, this function initializes the chip to work as a 14443A on this technology. So also there are some functions for waiting the events from HAL, also to transmit frames and to receive frames in both polar mode and in listener mode. Also we have some kind of helper. It's placed in the Fourier NFC timer. Okay, I want to stop here and speak about NFC frames. So on the screen you can see the NFC frames. You can see the one with deep modulation. It corresponds to the polar modulation, and with less deep modulation, it corresponds to the listener frames. Basically, okay. Can you hear me now? Okay.
Yeah. So, sorry,
okay.
Shallow, I think is the word you were looking for.
Okay, sure. Okay, thanks. So basically, at some point, all protocols define this FDT constant. It's frame delay time. Let's have a look on the first picture. Here is the frame delay time for the listener. This is a minimal amount of time that listener should wait before transmit its frame after it receives the frame from polar. Also, the same thing is defined for polar. It's called frame delay time polar. It's the minimal amount of time that the polar should wait after it receives the listener frame before it should send its polar frame. Also, there is a so-called pole FDT. It's defined how much time polar should wait before two consecutive polar frames if there was no listener frame between them. And also the guard time. It's the minimal amount of time for polar to wait after it turn on the field and before it can send its first polar frame. To meet this frame delay time, we have the block TX timer. So basically, you can think about this frame delay time as the time that either that listener or polar should wait before it can send the frame. And
So when speaking English, this would be like the amount of time you wait for the other person to shut up before you start talking. And if they say or ah, then that's like, they're still they're still in charge. They haven't stopped talking yet.
Yes, you can think about it like that. And also, so we have two dedicated timers for this. One is block TX time timer to match this FDT constants, and another one is frame wait time. So basically, the protocols define the frame wait time. It means that after the poller send the frame, send the command, it waits for the response for defined amount of time. And if this time expired, the poller should think that okay, there will be no response, and should run its state machine further. Basically, there will be an error, the timeout error. And these timer helpers are placed in FuriHal NFC timer. Okay, I think it's all about the HAL part. Let's see the worker. The worker API is placed in the library nfc.h. So it has a common structure for our code. So it has allocation method, the free method, the configuration. So when you want to allocate the poller or listener, you should call this function to configure the HAL. And you should set up the timings here. So all these functions allows you to set the timings that I will talk about on this slide. And the worker part, worker layer, will meet the timing requirements. After everything is done, everything is set up, you can start worker, and you can provide the callback, and after that the thread will be spawned, and all events will be emitted to the callback you register here. After you're done, you should call the stop function. Also, there are some functions that you can use only in the callback. So, like poller tx rx function and listener tx function. So the common work here will be that you start the worker, you will receive some events, you will process these events and call these two functions from the worker thread. Okay, and there are also some technology-specific functions which are basically expands the functionality of these two functions. For example, for MIFARE Classic poller, we should control the parity bits, and that's why there is another function here where you can manually put the parity bits to be transmitted as a poller. Okay. That's all for the worker part. And now the most interesting part, the protocols. So we have a tree structure for our protocols, as I mentioned earlier. And we have the definition for all of these protocols in NFC protocol.h file. There is just enumeration for all these protocols, and in implementation part we have the registration for these protocols in a tree format. So basically, you can see here. Let's have a look on ISO 1444-43 3A protocol. So each protocol has the parent protocol and the children protocols. So this protocol is the base protocol. It means that it doesn't have any parent. And there are some children protocols which are stored in the array. So for ISO 1444-3, there are two protocols. It's 1443-4A and MIFARE ultralight. And the same thing is done for every protocol. All of them are registered here. Some of protocols have parents and have no children. Some protocols have both parents and children, like this one, 1443-4A. And some protocols just don't have any parents and any children. For example, this ST25TB. If you want to add another protocol, you should, first of all, you should identify its place in this hierarchy. So if it doesn't have any protocols, you put it on this layer. If it's based on some protocol that we already have, you should put you should put it as a child for the based protocol. After you define the hierarchy for the protocol, we should work on protocol data. So when you implement a new protocol, you should think about the data management. And there is a helper, there is an NFC device model that helps you to write the data managed for your protocol. Let's have a look on this file. So we have NFC device base file where there is a declaration for the function that have to be implemented for a new protocol. You should add the allocation function, the free function, and other like reset, copy, verify, load. Okay, I will not tell about all this function. You can you can see the documentation here, but in general, we have this set of functions that have to be implemented for a new protocol. After you implement all these functions, you have to register this API for these functions in the NFC device devs. So here you can see that let's see the implementation for for MIFARE ultralight, for example, protocol. So we have this structure, and we register all the functions that are implemented in this structure, like data allocation, free, verify, save, load, and all of this function. We put it in this structure and register this structure here at NFC devices. And after it's done, you can use the NFC device API. So basically, when you allocate the NFC device, you can set data. Yes, you can set data for this device. You should put the protocol itself as an argument and the const pointer to the data. And after that, you can use these functions to manipulate your protocol data. So in other words, you can consider these functions as virtual methods, like in C++. And there is a wrapper as an NFC device model that internally calls this function that are implemented for your protocol. And you can work with your data at application layer. Okay, any questions with that? Is it clear, or maybe we should? Maybe it's not clear. Please
So
tell
I've
me.
got some questions. So something like an NTAG 215 uses the MIFARE ultralight protocol, so we don't need anything NTAG 215 specific. But the NTAG 424 is a Type 4 device, but it's not a MIFARE. And what I was kind of curious about is the only thing that an NTAG 424 can do is basically store an NDEF message. Like it's sort of like DeskFire's really dumb cousin. So what I was wondering is if I wanted to add like NDEF feels kind of like application level. It feels like it's above some of these. So on one hand, I was thinking, oh, maybe you would add in NTAG 424 support as another child of ISO 14434 4A. But another part of me was thinking, maybe you would just use that directly and you would just like make an NDEF app that just looks for NDEF and it doesn't matter what the tag type is. What's your thought? I mean, would that when NTAG 424 go into the hierarchy or would it just go into the application?
Okay, I think that it should go into hierarchy. So if you say that it's based on 1443 4A, it should be placed somewhere here, because if you want to read this tag, you should start the poller and manage events from the lower layer. So I think that I'm not familiar with these tags, but I think that in order to read something from it, you have to pass the activation procedure for this from this layer and this layer, and after that you can send the protocol commands for this NTAG 424, right?
Mm-hmm.
Yeah, so idea is that each layer in the hierarchy solves some specific set of your problem. So let's say it's starting with finding card on the physical level, then let's say 3A to perform anti-collision and things like that, and then 4A, and then your protocol. But there are sometimes you have things like sleeves. It's the most sleazy protocol ever, and it is kind of NFCV, but it's, I mean, the amount of things that was fucked up inside of the NFCV by sleeks is too big. And at some point, you may tell to yourself, okay, I don't want to base this protocol on NFCV. Is 15693, and instead I want to just implement the whole thing in one separate package. So it will be separate sleeks package. Yeah, and when we started to implement sleeks, we thought, okay, it looks like an FCV, let's just do that. And later, Georgi found that it's actually was a big challenge. So yeah, keep in mind what exactly you're implementing, how conformant it to standards. Is it fucking up for lower levels or not? And if it requires too many changes to lower levels, then probably you want to put it aside as a separate protocol.
Okay, thank you. Okay, let's move on. So you want to implement new protocol. You think is about the data structure. After you define the data structure and implement all the functions to work with them in NFC device, you want to make the protocol listener and poller. Let's start with the listener. We have actually the simple structure here, the similar structure with the listener part. We have also some kind of virtual methods for the listener functionality. We have so if you want to add a listener, you should implement these functions. So listener allocation, free, set callback, run, and get data. So let's talk more about set callback. Basically, when you start set callback and run methods. So basically, when you start the NFC thread, NFC worker, it will spawn events, and on each event, you will receive in the callback this event, and you will run the state machine to process these events and to spawn your own events on your protocol level. So the processing of these events are done in the run method, and also the listener stores the another callback with this function. So if you run this function, you put another callback here, and if you create some events, you will pass them in this callback. So we can see the picture here, how it works with emulation. So for example, you want to emulate, let's say, MIFARE ultralight. The application will allocate the NFC listener with the MIFARE ultralight protocol and start this listener. After that, the NFC worker will be spawned, and it will be waiting for events from HAL. After these events received, the worker will pass these events to the listener for this chain. So first event will come to the base listener. Base listener will process this event in a run method and spawn its own event for the upper layer listener. And so it goes step by step through the listeners to the application. And application itself process the events from the higher level listener and return the comments. And these comments are passed all the way down to the NFC worker. So if you want to implement listener, you implement these functions, register them in NFC listener devs. Okay, you can see here that some protocol doesn't provide the API for, doesn't implement these functions. It means just that Flipper doesn't support emulation for these protocols. But let's see, for example, MIFARE ultralight listener part. So here you can see implementation.
Question on that.
Yes.
So the hardware doesn't support like emulation of B, so that's why 3B and 4B are null. But on line 18, Desfire being null, that's because it hasn't, like, it could implement that, but the code hasn't been written. Does that make sense?
Yes, correct. So in theory, we can implement MIFARE Desfire, but frankly speaking, there is no much sense in that because MIFARE Desfire is protected protocol. So in order to emulate it completely, you should know the keys and.
Well, I think there is an argument, because I've talked to people about this stuff before. If there was perfect Desfire emulation, then you could have the Flipper emulate and you could enroll the Desfire into a system. So that way it was given all the keys and everything. Not the most popular idea and everything. I just want to throw out there, like, this null on line 18 is different than the other two nulls.
Yes, you're right. So in theory, yes, we can implement emulation for MIFARE Desfire. Feel free to contribute to our project. Also, you can see that we have emulation for ISO 15693, so NFC part, and it's not supported by the chip from the I would say generic point of view. So the chip from the box doesn't support emulation for this part, but we use the transparent mode here, and the emulation work with the transparent mode of this chip. It's possible because NFCV signals and timings are relatively slow, and we can manage to modulate the signal by toggling the GPU, and we will we will meet the timing requirements. Okay, let's have a look on some kind of listener. So here, this is allocation for MIFARE ultralight listener, the free part, and let's have a look on the run method. So basically, you can see that the run method for ultralight protocol will receive the context. The context is the MIFARE ultralight listener instance, and it receives the generic event. Let's have a look at the generic event. It consists of 3 parts. First of all, the protocol that spawned this event, the generic instance. It can be the protocol poller or protocol listener instance, and the event data. So event data is defined by the protocol itself. For example, you can see here that we cast the event data from the NFC generic event to ISO 14433A listener event, which is defined in public API of this protocol. So here you can see that there will be some kind of events like field off, or the card was halted, or we received the standard frame. which means that the frame consists of correct CRC, and just received data when there is just frame with incorrect CRC. And the task for run method of the child protocol is to process the events from parent protocol, do some stuff, and emit its own events for the upper layer. Okay. And after we process this event, we return the NFC command. The NFC command will control the lower level. So it's this command passed all the way down through this hierarchy, and eventually it will control the worker part. Okay. Do you have any questions about listener part? How it's done and how to implement another listener? Okay. I guess no questions here. Let's talk about Polar. Polar is quite similar to the listener. So we have also these events and comments. Actually, the functions to be implemented for the Polar are quite similar. So we have also this alloc and free functions for the Polar. We also have the this run method and set callback. And another method is detect. So all Polars have to implement this method that are this method is called by another module, NFC scanner, which helps to detect the protocol after when you press the read button in NFC application. We'll talk about it later. So basically, the flow is very similar to the listener part. You have these functions to implement. Once you implement them, you register these functions in NFC Polar devs. So here we have no null because all protocols have to implement this the Polar part. And after that, you can allocate the Polar. And here you will see the clean API. So when you allocate the Polar, you you pass the protocol. When it's allocated, you can start the Polar. You can pass the callback, and in this callback, you will receive the events from the protocol that you allocated. You can process these events, and after you're done, you just call NFC Polar stop. After you finish your Polar part, you finish polling the NFC tag, you may want to get data from the Polar, which consists of the data that actually was read, and this one, get Polar data, and you can save it in application layer, and so on. That's how it's working now. We can look at the example to see how it's done for different protocols. Let's have a look on the structure for these protocols. So let's start with the simple one. The ISO 1443 3A. Okay. Here we can see the protocol data. For this protocol, the data is very simple. You have UID, UID length, ATK, and SAC. There are these are the functions that are implementation of the NFC device base functions prototype. Let's have a look on the Polar. So the Polar part will receive the Polar state machine will receive events from worker. Actually, it will process only one event, the Polar ready event. It means that the worker part already turned on the field. It waited for the guard time, and it's ready to send some Polar frames. So if the worker part is ready, it spawns ready event, and in this protocol state machine, we we check our state. If we didn't pass activation yet, we perform activation. It's anti-collision process during which we fill the data. We read the UID, ATK, and SAC, and when it's done, we change the state, and we start spawning the ready event. Yes, so once we pass anti-collision, we can we spawn in this ready event for the upper layer protocols. And let's have a look, for example, the child protocol for this, the one, for example, MIFARE ultralight. Okay, MIFARE ultralight Polar. So also we have the run method here. Here we expect events from ISO 1443 3A protocol. We process event from that layer. Okay, for example, if there was some error for the lower protocol, we will fail on this layer as well, and spawn the fail event, read fail event for the application. And if there is no error and the lower layer protocol is ready, we run our state machine. These are the handlers for the state machine, so we will not go into each one, but in general, this is the place where the MIFARE ultralight reading is done. So first we have the idle state on the first iteration, on the first call of run function. Then we perform read version command, and okay, let's have a look. For example, we we call read version. If there is no error, then we go to the state, which is called get feature state. So we get the features of the NFC tag by the version that we read. Sorry. If there is an error, that means that probably this tag doesn't support read version command, and we go to another state. We, for example, first we detect the ultralight C tag. For that, we perform the authentication. If there is no error, then okay, we detected the ultralight C, and if it's not, then we should check for NTAG 203 and so on. So after we detect the exact type of the MFR ultralight or NTAG, we go to this state where we identify the tag features, and then we go to the read signature state, where we read signature. After that, we read counters, tearing flags, and so on. Then we read pages, and after that, we will end up in one of these two states, which is read fail or read success states. And we will emit, we will pass these events in the callback for the application. And the application processes this callback and display information and so on. This is how Polar and Listener works. So this is, I think, the most important part for the new stack. We can we can see here the clear layers for each protocols, and I think it's much easier now to add new protocols. For example, this protocol was this protocol ST25TB was implemented by our community member. So he implemented this protocol even before we finished our documentation, which gives me a hope that the code is quite clear and community will add even more protocols in future. Okay, and a couple of words about NFC scanner. So you can consider this model as a helper. It has its own events. Actually, it has its own worker, but it's the implementation detail. But in general, you can allocate NFC scanner, and you can start it. You can pass the callback, and the callback will be will pass you events, which are basically sorry. The callbacks. In callback, you will see the array of protocols that was detected by NFC scanner. So it helps us to deal with, for example, multi-protocol cards. There are some NFC tags that support different technologies, and now if you read them, the Flipper application will give you an option to read this tag with a specific protocol that you choose manually. Okay, this is all for the protocol parts. I have something to say about NFC application, but before that, do you have any questions? Maybe you want to look at something at implementation for some models.
An important thing to mention is that new stack will allow detect multi-protocol cards. It's like really big achievement because previously you either will have to know that this card supports multiple protocols and you have to select specific one. Yeah, now you will be told that this card is multi-protocol. For example, when I'm reading, let's say I have an iPhone, I have iPhone with FedEx transport card and then a bunch of other. And when I will try to read, I will get that, okay, we have A, B, and FedEx. And we will ask you what exactly you want to read.
Yes, there are actually many multi-protocol cards on my table too. So this is a great option to choose specific protocol. Okay, now let's have a look on application layer. So I will just cover some changes. Compared to the previous implementation. So basically there are two things that changed. The first one is okay, we called it the protocol support on application layer. It means that in our NFC application there are some sense that are common for all protocols. And basically, we have also this file, NFC protocol support base, which declares the functions that have to be implemented for a new protocol. So that NFC application will call the protocol-specific implementation and, for example, display the data from this protocol on the flipper screen. So we have here the full set of common stands, and their implementation for this stands are in protocol support folder. Let's have a look on MIFARE Ultralight. Actually, yes, here you can see the structure for this base protocol support functions. We register the implementation here, and this function, you can think about this function as a protocol renders. So basically, when you enter the info scan, for example, you expect to see the information about the protocol that you read. And the part for displaying this data is not actually the library part. So the task for the NFC library is to introduce the data structure, the polar part, which fills the structure after reading, and the listener part, which use this data for emulation. But the displaying of this data is not the library part. It's an application part. For example, if somebody wants to make another NFC application, he can use our NFC library and rewrite the application part, which will render the data differently. And that's why we introduce this protocol support part on application level just to match this different rendering part for different protocols. Okay, and also a new thing for the application is NFC plugins. we have the plugins API, the plugins interface here. So it consists of 4 fields. The protocol, which corresponds to the supported card, verification method, read method, and the parse method. So the verify and read methods are optional, and they are called once NFC scanner detects the protocol. For example, we have we have Troika card, which is the MIFARE Classic card, and when we detect the MIFARE Classic protocol, the application will load these plugins one by one. It will compare the detected protocol with the protocol field of this plugin, and if it's matched, and also if the verify and read methods are implemented, it will call these methods. So first, it will call the verify method, which actually verifies that the card that we are reading is actually the supported one. So for example, for Troika card, we will try to authenticate for the specific sector with specific key, and if we succeed, we go to the read function, which will read the whole NFC card with the keys that are placed in the plugin. And if the read success, the NFC application will call the parse function, which will turn the MIFARE Classic data into human readable format and display, for example, the number of this card and the balance on this card on the screen. So as I said, the verify and read methods are optional, but the parse method is mandatory. So if you want to add a plugin, you should definitely define the protocol and the parse function. For example, we have a PAL. I think it's used in Sydney as a transport card.
Yep, it is.
So let's see the implementation part. So the protocol is MIFARE Disfire. We have no verification and read methods here, but we have a parse method which receives the data that was read by application, and also it will go through the internal files and convert these files into human readable format, displaying the balance, the serial number, and some other interesting stuff. So all these plugins are actually the Flipper application library, I believe. They are built as a separate not application, but we have the plugin format for these applications. And if you want to add another plugin, you should implement it and put the description into the NFC application manifest. Okay, and Yes. Okay. So what's next? We released the stack. What's next? Now it's time to gather the feedback. We already see that the API that we give is not convenient enough for some users, so we will improve it. We discuss it on the GitHub, and we will improve the API. Also, we are planning to support more protocols. Currently, we are working on Felica. Now Felica has only basic support, so we read only UID part, but we want to be able to read the full dump and to emulate it. And another interesting topic is the sniffer part. So maybe using the transparent mode, we can achieve the sniffer functionality. So acknowledgements, yes. I want to thank Georgi Surkov, Artur, and Astra. They are NFC developers in our team. Alex, Dr. Zlo, Vanya Hedger, they are architecture advisors. So also thanks to our QA team, and of course thanks our NFC community who build new applications and help us to make NFC better in Flipper. And that's all from my side. Thanks for listening.
Are you guys gonna? Have you already published this Miro board publicly? Will you be?
Not yet, but I see no
And
problems
we
to
can make it
publish
right now.